Have you ever really thought about where our power comes from? Or the fuel in our cars? So much of modern life relies on these massive, unseen machines. Well, today, we're going to go inside them to explore the incredible physics of heat exchangers.
All right, let's just dive right in. When you look at a sprawling refinery, it's like this whole city made of steel, right? And these machines, well, they're its vital organs, just humming away silently. But the real story, the physics that makes everything tick, that's happening deep inside, on a scale we just can't see. So, what is actually going on in there?
You know, these machines are the absolute workhorses of industry. I mean, whether we're talking about making electricity or refining fuel, they have one core job: to move huge amounts of heat from one fluid to another. They are quite literally the industrial heart of our world.
So let's break one of these things down. The big outer casing, that's the shell. Simple enough. Inside that, you've got this super dense network of pipes. That's the tube bundle. The tube sheets, they're what hold it all in place. And then you have these plates, the baffles. They're placed in there very strategically to guide the fluid and make sure it flows where it's supposed to. It's a really simple, incredibly tough design, and it's been perfected over decades.
Okay, now for the really cool part. We're going to leave all that massive steel behind for a second and go microscopic. Inside this transparent model, we can actually see the invisible dance of fluids that makes the whole thing work. So when things are moving slowly, something pretty beautiful happens. The fluid moves in these perfectly smooth, parallel layers. We call this laminar flow. It's all very orderly, very predictable, kind of like a disciplined army on the march. But here's the catch. Those layers barely mix with each other. The fluid right up against the pipe wall is almost completely still, and it acts like a little insulating blanket. But watch what happens when we start to speed things up. That orderly march just dissolves into this chaotic, swirling dance. This is turbulent flow. You get these eddies and swirls and just all kinds of vigorous mixing. Now, it might look messy, but here's the secret. That chaos is often exactly what the engineers are trying to create.
So why does any of this matter? Well, it all comes down to heat transfer. With that smooth, laminar flow, heat has to slowly kind of conduct its way through the fluid layers. It's not very efficient. But in turbulent flow, all that chaotic mixing physically carries hot fluid to the pipe wall and yanks cold fluid away from it. Think of it like stirring a hot cup of coffee versus just letting it sit there. The chaos, that's the real key to efficiency.
So we've got the flow figured out, but what's the end result? Let's switch over to a thermal view so we can actually see the energy in motion. This is the whole reason these machines even exist.
What you're seeing here is pure physics in action. Heat always moves from hot to cold. That's a basic rule. And you can literally see it happening. The fluid comes in, glowing red hot, and as it gives up its energy, it cools down and leaves as this stream of blue. The entire goal of the design is to make that color change as dramatic and efficient as possible.
But you know, even the most perfect design has an unseen enemy. It's this slow, relentless process that builds up over months and years, and it silently chokes the system's performance. And that enemy has a name: fouling.
It all starts with a perfectly clean surface. But over time, things like minerals, sediment, even biological growth, they start to build up. This gunk acts like a layer of insulation, and it just blocks heat from getting through. As it gets worse, it narrows the flow path, and before you know it, the whole system's efficiency just absolutely plummets. So how do you fight back against it? You fight it with this. Incredibly high-pressure water jets that literally blast away years of built-up fouling. You can see it just being stripped right off, revealing that clean metal underneath. This is what it takes to get the machine back to its peak efficiency. So, when you know all these challenges, the details of flow, the need for heat transfer, and this constant battle against fouling, how has the engineering evolved to deal with it all? Let's take a look at the designs. Here we have the two main players in the game. On the left, you've got the classic shell and tube. It's big, it's tough, and it's incredibly reliable. On the right is the more modern plate exchanger. It's way more compact, and those corrugated plates create massive amounts of turbulence, which makes it hyper-efficient. It's a classic engineering trade-off, really. Brute force and reliability on one side versus compact, high-tech efficiency on the other. So, when you think about it, from these massive industrial structures all the way down to the chaotic dance of molecules, heat exchangers are really a testament to our mastery of thermodynamics. But in a world that is always demanding more and more efficiency, you have to wonder, what's next? What new designs are going to power the future of these quiet, essential giants?